In this video, we'll be discussing the general linear f-test, which is an extraordinarily flexible tool that we'll be taking advantage of throughout the rest of the class. So the general linear test involves comparing two what are called nested models. Now, nested models refer to two statistical models where one of the models has all of the variables and more of another one. So, for example, we might have just an intercept only model, so y equals beta plus error, so just intercept. And then we would have something with intercept and the slope. So in this case, this first model would be nested within the second model because the second model has all of the variables from the first model and more. Now, the general approach of the general linear f-test is going to be to look at the error that's present in both of these models, but it's important to understand up front that the model with more variables will always have less error than the model with less variables. So this model, even if x has nothing to do with y, theoretically, just the random error component involved with x is going to give this model slightly less error than the first model. So the goal is to determine not just if the error is smaller, because there will always be smaller error with a model that has more variables in it. Always, 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 every time. The goal is to determine if the error drop is enough to be worth adding the extra variable. So again, this is an extremely versatile test that we can do, and it's because you can do this with any set of nested models. And what we test is the difference between the models. So in that previous example, we had one with just an intercept, one with an intercept and slope. What we're testing is what's the impact of the addition of a slope parameter. So when we get to fancier models where we may have lots and lots of variables, we can look at nested models and say, well, what's the impact of anything that's missing in the smaller model? So we just start with a big model, we cut out whatever we want to test, and then we have the smaller model, and the general linear f-test allows us to determine, are the things we cut out important or not? Again, the idea is to compare the drop in error associated with adding the variables to the model. So when we add variables, if the error drops far enough, then the model with the smaller error is labeled statistically significantly better. So to perform the general linear test, first of all, we want to be able to define our hypotheses. So in this case, I'm going to test the slope parameter. I want to see if the slope is 0. And again, we can do this with multiple parameters at the same time. It's one of the cool parts about the general linear test, but I'm just going to focus on, is the slope 0? I'm going to create two models. I'm going to create the full model that has the slope, and then I'm going to create the second model that removes the slope. So again, 0 times x, this is that reduced model that we showed earlier, y equals beta 0 plus epsilon, because the 0 times x disappears. After we have this, and actually in general, the test statistic for the general f-test with a full and reduced model is the sum of squares of error for the reduced model minus the sum of squares of the error for the full model, divided by the degrees of freedom from the reduced model minus the degrees of freedom from the full model, all divided by the sums of squares for the full model divided by the degrees of freedom for the full model. And again, remember that the sum of squares of error for the reduced, that is the amount of error in the reduced model, will always have more error than the sums of squares of error for the full model. And again, this is because when we add variables, it always takes some amount of error away. The question with the general linear f-test is, did you take enough error away for this to be considered statistically significant? Now, again, we're testing if you have enough less error. We prefer smaller models. So unless there's a reason to have that extra variable in there, that is, unless you've dropped the error a meaningful amount, then we're going to stick with the smaller model. So if adding a slope parameter only drops the error a little bit, not statistically significant, then we're going to leave it out because smaller models tend to be better. Now, the law of parsimony, or Occam's razor, discusses how simpler things not only are easier to interpret, that's an important component, but also they're more likely to be correct in general. That is, they're more accurate and likely more descriptive of what's actually going on. So when we're constructing these tests, the goal is to compare the bigger model to the smaller model, unless we have a reason to stick with the bigger model. And that's what statistical significance in this test means. If we have statistical significance, then we would go with the larger model. If we don't have statistical significance, then we would go with the smaller model. So that's what we're looking for. And again, the reason we would go with the smaller model unless we have a statistically significant difference is because we tend to prefer smaller models, especially if the smaller model does just as good of a job as the larger model. And that's what a lack of significance would mean. If we don't have a statistically significant difference, what that means is that we can't tell that the larger model's doing a better job. We can't tell that the larger model has a non-zero impact. So if we can't even tell the difference between a smaller model and a larger model, or a model with less variables and a model with more variables, then why would we use a model with more variables? It's more complicated. It's harder to interpret. It's probably dealing with more complex concepts, which may or may not be related, so it has a higher tendency to be incorrect. If we have, again, multiple models and we have a smaller one and a larger one, and the larger one doesn't do any better with the smaller one, we tend to stick with the smaller one. That's this idea of the law of parsimony, and it's how we use the general linear test. All right. So correlation, recall R is the correlation coefficient, the Pearson correlation coefficient, and R is between -1 and 1. What we didn't talk about when we first talked about correlation is that correlation is directly tied in to tests of the slope parameter. And actually, the correlation can be calculated using the slope statistic. So if we have the slope, we can calculate the sample correlation by taking the slope times the sum of squares for x divided by the sum of squares for y. So SSX over SSY, square root of the sum of squares of x over the sum of square of y. And that gives us our correlation coefficient. Now, if that gives us the correlation coefficient, then what we end up having is that when we look at the coefficient of determination, or squaring the correlation coefficient, we end up with the sum of squares regression divided by the sum of squares of total. And if you look at this, remember that this is the sum of squares total, is just the sum of squares of y. So we end up with the sum of squares regression divided by the sum of squares total, which is 1 minus the sum of squares error divided by the sum of squares of total. So you can literally think of the coefficient of determination. It really is, if you look at sum of squares regression as the amount of variability in the model, and sum of squares total as the total amount of variability, this literally is the proportion of the sum of the total amount of variability explained by the regression model. So quite literally, we can look at this as the percentage of variation in the total data explained by the model. And again, that comes from this equation. And one of the reasons we bring it up now is because we couldn't talk about it when we initially introduced the coefficient of determination in the correlation chapter. But now that we've talked a little bit about these sums of squares, now that we've talked about the regression coefficients, we can come back to this and see why this interpretation comes to be this way. Don't just trust me. Look at the derivation to see this literally is the percentage of variation of the total variation explained by regression. All right, so real quick, now that we've talked about that, now that we've demonstrated that, I want to call out some potential misunderstandings. First of all, having a high coefficient of determination doesn't mean that the model is useful. It also doesn't imply that the fit is good. You can have high coefficients of determination, you can have lots of variation being explained, and the model can be terrible. You can also have lots of variation explained and have a pretty poor fit. It's very possible to have that happen. And kind of in the from the opposite direction, you can have small coefficient of determination and realize that there is a relationship between x and y. That is, small values of r squared doesn't mean that there's not a relationship between x and y. Just like a small correlation coefficient doesn't mean that x and y are unrelated. It doesn't. all that it means is that there's not a linear relationship between x and y. And it's important to remember from back when we discussed our correlation coefficients that we really focused on that term of linear. When we talked about Pearson correlations, we focused on the term monotonic. When we focused on Spearman's correlations, but when we say that there is a small correlation, many students jump, and frankly, many professional researchers jump to say, oh, there's no relationship between these variables. That's not supported. All that we can say is that there is no linear relationship, or that there isn't a strong linear relationship between those variables. So don't get mixed up here. The coefficient of determination and the percentage of variance explained is a very handy tool, but it's not the be-all end-all of data analysis, and we don't want to fall into some of the understanding traps that occur when people just focus on that particular statistic and don't do things like plotting their data, checking assumptions, looking at alternate models, and looking at alternate methods of analysis. All right, so this ends lecture 3. In the future, we will be looking at model assumptions and diagnostics, and then jumping into how do we actually fix models when assumptions break. So the next lecture is going to be completely talking about what are the assumptions made in simple linear regression, and how do we assess those assumptions.